Good evening, everybody. So tonight's talk is about descriptive data analysis, which includes the different types of data that arise in clinical studies, and then mainly the descriptive statistics on these data, graphs and numbers, and if you are writing an article, then how to report the descriptive statistics of your data set. So statistics, as we all know, it's the study of making sense of data. So you have some data and, okay, what does the data tell me? What's the story behind this? It includes collecting data, mainly starting with even the design phase, and then describing, which is the topic of tonight's talk, and then analyzing, interpreting the data, so going one step further, and at the end, reporting, in order, again, to help people make decisions when they are faced with uncertainty. And when we talk about biostatistics specifically, it's the statistics on data related to medical and health fields. There are several areas of statistics, two of which are the descriptive and the inferential. The descriptive is what we will be discussing at length tonight. And they consist of methods of presenting, summarizing, and describing the data. So we do tables, we do graphs, some numerical summaries to describe and summarize and present in an understandable way our data set. Now, inferential statistics is another area, and this is when we move one step further and we start using our descriptive, using what we got in our sample to conclude and come up with generalization of our conclusions, like confidence intervals and p-values. Some basic definitions before we move further. So we are interested usually in statistics. You have an interest in mind when you do research is a certain population, which is the collection of all subjects of interest. For example, you might be interested in all Lebanese males 50 years of age with coronary heart disease. Now, populations in general, they are impossible to collect. And if not impossible, they are very impractical to collect and very costly. So what researchers do instead is rely on samples. So a sample is the subset of the population of interest. So in our population here, our sample would be, one sample would be 100 randomly selected Lebanese males that are 50 years of age with coronary heart disease. They exactly are like the population of interest. Now here I will stop a second and talk about randomly selected. So there are several ways to select a sample. One of which is random selection, which is the best way, yet not very practical in many situations. But this is the best way to collect a sample, and statistics actually are based on the assumption of having a randomly selected. Now, on this sample, we need some variables of interest, some characteristic of interest that we need to measure. This is what we call a variable. So it's called a variable because it varies from one person to another. On this particular sample, for example, males 50 years of age with coronary heart disease, one variable of interest, like a trivial variable of interest, would be systolic blood pressure. And then whatever those sample subjects will score on this variable, for example, 140 millimeters of mercury, 160, 110, these are called our data. Now the data, they can have several types. So one type of the data, like the systolic blood pressure, for example, when it's numbers, it's numerical data, we call it continuous or quantitative or also interval data. So these are the variables that can take any number. Like blood pressure, as I mentioned, like weight in kilogram, like height, age in years, income. So these are continuous data or interval data. We can collect other types of data, which is categorical data. So in this situation, the variable cannot take any number within a range, but it takes certain numbers actually, only a limited number, and the number here is a category. So the number by itself does not have a meaning. It's used to represent a category. For example, gender. It's male or female. It's a limited number of categories. Even if I assign a number to gender, if I assign males 1 and females 2, the numbers themselves, they don't have any meaning. And I can do the other way around, males 2 and females 1. Same for marital status, same for symptom severity. Now, within categorical variables, we can actually divide it into two groups, nominal variables and ordinal variables. So when the groups themselves are not ordered, like gender, this is called a nominal variable. Or marital status. So it's not that I'm moving from single to divorced to, I'm not moving in a certain order. So this is called nominal variable. Now, but sometimes the categories I am using are actually do have a certain order, like the symptom severity. I'm going from minimal to moderate to severe. So here, in addition to only having categories, I'm adding here something that the categories, one is higher than the other or lower than the other. So this will be called ordinal data. Now, if you look at this example here, I have a data set on, it's actually on survival analysis for a set of patients. Now, I selected here a few variables. If you look at the patient ID, this is one variable. This here is a nominal variable, for example, because it's like a category. The number itself does not have a meaning. I can put 11 for the patient, or I can put, it's the patient number 11,000. This does not make any difference. Now, for the vital status, dead or alive, this is two categories. It's a nominal variable. Same for gender. Now, age, it's an interval variable because it can take any number here, and the number itself, it has a meaning. 40 years of age cannot be 50, it's 40. Same for BMI, and I have at the end also the hospital admission date. This is actually a new type of variable. I just wanted to include it here so you know. It's date variable, and these variables are mainly used if later you want to do some survival analysis. So you are counting days of hospital stay or days until recurrence of cancer and so on. So why did we spend some time talking about data actually? It's because it's very important to determine the nature of the variable under investigation and the type of the data. Because later, when we want to describe it, I have some descriptive methods for categorical and for continuous. So to start with, it's important for you to know what is the type of the variable you are interested in. Not only for descriptive, but for later, if you want to do other analysis. The type of the variable is whatever dictates the type of analysis you want to do. Now, I can transform my data from continuous to categorical. So for example, if I look at my BMI in the previous example, BMI is only, it's just a set of numbers, so the BMI is a continuous variable. But if I collapse it in categories, I take them, for example, BMI less than 20, everybody who has a BMI less than 20 in one category, and I call this as my group 1, and then I continue and so on, I make those three groups, then this becomes a categorical variables, group 1, 2, 3, ordinal specifically. So I can move from one type of data to the other depending on your interest in your research. Do you need to have BMI, for example, as one value, or do you need it as groups because you think those who have BMI less than 20 are similar to each other, and then from 20 to 30 again, and so on. Now, for descriptive statistics, we can do graphical summaries or numerical summaries. Now, we statisticians, we are known to like graphical summaries and to like graphs. The first rule, actually, in any statistical analysis is to draw the picture. Why do we do that? Sometimes, mainly, you record, for example, a value of 999, and you're not aware of that value is actually a missing value. So if you don't plot it, sometimes it's hard for you to detect it as it's a 999 for age, for example. So usually we start by graphing the data. For categorical data, the graphs that I am going to talk about are the bar graph and the pie chart. And for continuous data, and here actually the graphs are much more informative than in categorical, we do the histogram and the box plot. So as I said before, we separate. Categorical data have a certain set of graphs to be represented by, and continuous have other graphs to be represented by. Now the bar chart, these are simple graphs that you have seen, I'm sure you have seen before, and you have seen many times. So they are here used to visualize the counts, actually, that we call also frequencies. So how many in my sample are males, how many are females. Instead of putting the numbers, bar graphs are nice, especially if you are presenting a poster, for example. You can use them in a bar graph. So they consist of a series of non-adjacent bars. So here the bars are non-adjacent because there is no category between male and female. There are males and females, period. And they represent the categories of the nominal variable that I am presenting, or the ordinal. And the height of the bar will represent the count, not only the count, I can also put the percentage. So I have 50%, for example, males, and 50% females. The same here, data, I can represent it in a pie chart. In the pie chart, I do only the percentages and not the counts. However, again, statisticians usually advise to stay away from the pie. If you look at the Wikipedia page on pie charts, you can see this actually. Looking at the bar graph, you can see the difference clearly. So I can see in the first bar which bar is the most frequent, and in the second I can see, and in the third. Whereas if I look at a pie chart, it's really, I can see them all the same. Now, if you have a poster and you think a pie chart is nice to be in the poster, this is fine, but in general, we prefer bar charts to pie charts. And the bar chart, we can put more than one variable on it. For example, here, I have two nominal variables, the gender, male and female, and the follow-up status, dead or alive. So here I have two clusters. The clusters represent the categories of one nominal variable, which is the gender. So I have a cluster for male, a cluster for female. And within each cluster, I have two categories, the categories of the other variable. Now, moving to continuous variable, one important plot to use is the histogram. Now, the histogram, what it does actually, it categorizes, if you want, the continuous variable. It groups it in classes of equal width. On the x-axis, like here age, for example, we put the quantitative values of my variable of interest. So here the ages, I can see in the x-axis, I have 40, 60, and so on. In the y-axis, like the bar chart, it has the counts. So how many people are in that category. Now, in the histogram, the adjacent bar, they are contiguous. So I don't have a gap like in the bar chart. And the reason here is that even if I don't have any column between 40 and 50, this does not mean that I don't have a category, 40 to 50 years of age. This category exists, but nobody in my sample fell in this category. So when we do a plot, again, mainly in continuous data, we ask ourselves questions because the plot will be very informative. So for example, one question I might ask is how many major peaks I have in the histogram. For example, in the one I have in the picture here, I can see one major peak. I can also ask myself if the data looks symmetrical, yes or no, or if there are any feature that stands out. So for example, do I have all the bulk of the data somewhere and then I have one column really far away from the others? So when you do a graph, you ask yourselves all these questions, because when you look at a graph, you are mainly examining your data. So when we examine our data, we look in the graph at the overall pattern, where is the bulk of the data lying, and at striking deviations from that overall patterns, if any. Yes, please. Yes. The
However, you can see that the bars are for certain.
Yes, the histogram actually.
So even we categorize
Exactly.
continuous.
Exactly. Yes. So the histogram here, it groups the data in classes, but we use it for continuous. But exactly as you said, it groups it. So it's like it categorizes it exactly. So when we look again at the graph, we look at the overall pattern, which when we look at the overall pattern, this means we examine the shape, and I will talk about these in a little bit, the center and the spread. And we also look, and this is an important feature, we look at, do I have any striking deviations from the pattern? Shapes of data, we can have several shapes. I'm gonna here only put a few of them that are the important ones. So symmetrical. Symmetrical data are preferred. We like to have symmetrical data because statistical methods are more robust and more available when we have symmetrical data. Symmetrical shapes, we have the bell shape. This is the very known bell shape or the normal curve. Whenever you will see more statistical talks, you will see that a lot coming, the bell shape curve. So this is a symmetrical curve. So if you put an axis in the middle and you flip the two, you like divide it in two and you flip the two over, you will get the same exact shape. But normal curve is not the only symmetrical curve. For example, I have on the right another shape. uniform. It's also symmetrical, but it's not normal. We have non-symmetrical shapes that are also specific shapes, like for example skewed data. Whenever the data, the histogram has a tail and it's not equal tails, I have one tail that is really longer than the other, this is, I say I have a skew in the data. Now if the tail goes to the right, I call this a right or a positive skew. If the tail goes to the left, I call this a left skew. And in my first graph on the left, not only I have a right tail, but I have, this is what I mean here, deviation. So I have those two little bars standing away. So these are potential outliers, and I will talk about outliers actually at the end of my talk. And now, also with shapes, I can have more than one major peak. So here, for example, I have two major peaks. And believe me, this can be very informative. Whenever you have a certain research question in mind and you see this shape, this is very interesting. Go back and analyze why you think you got those two major peaks, why the data fell, all of it in this column, dropped a little bit, and then again, it increased in this coming class here. So after graphical summaries, now I'm going to move for numerical summaries. And again, we're going to go in the same fashion. So categorical data have a certain numbers that we use to represent, and same for continuous data. Now for categorical data, and again, categorical data are data that have categories, like gender, like marital status. This is here very simple. We represent them by counts, which we call frequency. So how many subjects fell in this category? And definitely percentages. If I'm comparing, percentages are more meaningful than actual counts. For example, if I take my BMI group, and remember BMI was a continuous variable, but here I grouped it. So it became 3 BMI groups. For example, here I have 7 people falling in group 1. Now for simplicity, I use the total sample here as 100, and this represents a 7%, 64 in the second BMI category, 64%, and so on. So these are very simple and very trivial, the numbers that we use when we have a categorical variable to describe. When we move to continuous, there are actually a lot of variables that are used to describe continuous data. And we can divide them in two categories, measures of center and measures of spread. So the measures of center, they tell me where the center of the data is, and the two big measures of central tendency are mean and median. For the measures of spread, there are many, like the range, the standard deviation, the quartiles, and the interquartile range. So starting with the measures of central tendency, the mean is, we all know the mean. It's the average. We compute average on our daily basis. So this is the sum of all observations we divided by the sample size. This is the preferred measure actually of center in statistics, but it's not applicable all the time. Now the median is the middle value. So it's the value that divides my sample in two. So whenever you compute the median, what does it mean? It means that 50% of your data are below that value, and 50% of your data are above that value. Now, if we compare those two measures, the mean actually is sensitive to extreme values. So if you have one outlier in the sample, the mean will be immediately affected by that. The median, on the other hand, is not sensitive to extreme values. However, the median, to compute it, we use only the ranks of the variables. We do not, with the values, we do not actually use the value itself. So we do not use all the information in the data. For the mean, no, we use the actual value of the variable. If the data are symmetrical, mean and median are equal. So we don't have to worry about which measure is better than the other. In our actually data set, for example, if I'm talking about age, the mean age was 68 years old, and the median was 71 years old. So on average, my sample has 68 years of age, and I know that 50% of my subject had below 71 years old, and the other 50% is above, older than 71 years. Now the measures of spread, the most known measure is the standard deviation. It shows how much variation or dispersion exists from the average. So around the mean, what is the deviation from that mean of my sample? I can also use the range as a measure of spread. It's the maximum value and the minimum value, or sometimes we compute the difference between the two. Now, from the definition of the range, we can see that it is sensitive to extreme values, as the extreme values are going to be either the maximum, either the minimum. Other measures of spread that are very important measures are the quartiles. So here you want to know, you divide your numerical data in 4 equally sized parts. For example, you know which number has below it 25% of your sample. The 50% of your sample are below which number, and so on. The quartiles are Q1, Q2, Q3. So Q1 tells me it's the number that has 25% of data below it, and automatically this leaves 75% above. The second quartile is the same as the median, 50% of the data below and 50% above. And the third quartile, it leaves 75% of the data below that number. And in many situations, instead of using the quartiles Q1 and Q3, we use what is called the interquartile range, which is either the two numbers listed next to each other, either again the difference between the two numbers. Now, if you are interested not only in which number leaves 25% below, 50% below, or 75% below, you might be interested in seeing which numbers leaves 90% below. You can also do that, and these will be called a percentile. So Q1, for example, will be the P25, the 25th percentile. Q3 will be the 75th percentile. You can have P90, P5, whatever is of interest for you. In our data, the minimum age, if we are still talking about age, was 32 years of age. The maximum is 92. Standard deviation is 14.4. So this means around the average, if you remember, the average was 68 years old. So around the average, your patient has, for example, 68 plus or minus 14 years of age. Now, I know that 25% of my sample are below 60 years of age, or 59.25. And I know also that 75% of my patients are below 81 years of age.
How do you calculate the standard deviation? How do you know that it's 14?
I did this using a software. I'm not including formulas actually here. Usually to find the standard deviation, every single observation, you subtract the mean from it. You subtract the average of the sample, you square it. So you do all this, and then you divide by the sample size minus 1. But I mean, any software can do these. Excel, I mean, these are simple stuff. Okay, a lot of summaries now, a lot of numerical summaries. I don't want to confuse you. There are summaries that are best, and these apply to every situation. Now, for categorical data, that's it, counts and percentages. For continuous data, usually we select a measure of center and a measure of spread. And what makes us choose which measure is the shape of the data. If I have a symmetrical data, the measures to represent this are the mean and the standard deviation, straightforward. If I have non-symmetrical data, so I have some skew in the data, I use in this case the median, because as we already talked about, the mean is affected by the skew, and the quartiles in that situation, into the quartile range. If you look, for example, at this journal article, they said in this case, they use the mean and the standard deviation because, as you see here, their variable is continuous and apparently it's symmetrical. This one here, for example, they represented the variable, the quantitative, not by mean and standard deviation. They did not do a mistake. They chose very well what they want to represent their variable by is the median interquartile range. Definitely, they again did the symmetry check, and the data was not symmetrical. If you look here, actually, it's very clear, and they're telling you that they used mean and standard deviation for continuous variables if the variables are normally distributed, which means symmetrical, and the median and interquartile range otherwise. And the qualitative variables, again, it's about percentages and counts. And this is another here example of on how to put these in a table. So they put the numbers and the percentages unless stated otherwise. In one table, if you have continuous and categorical variables, you go with the most frequent ones. So if you have more categorical, you go with counts and percentages. And then for the continuous, like here, you specify it in the table. It's mean and SD for age. Now, in other journal articles, they separate them. Continuous in one table, categorical in another table, or continuous in one column and categorical in another column, and so on. Any questions? Okay. Now, the box plot is the other plot that I wanted to talk about for continuous variables, because continuous variables, again, we talked about the histogram and now the box plot. The box plot, it's a graph but for numerical summaries. So we have 5 numerical summaries that we can put in a box plot: the minimum, the maximum, and then the quartiles. And it has this shape. And then if you see the minimum, the line of the minimum and the line of the maximum, these are, if I see any data point outside those values, if any value falls outside actually these, the software, any software that you use to draw a box plot, it will put a circle outside the box or a star, and this means that you have outliers in this situation. It will be represented by a circle or a star. The star is usually more extreme than the circle, so the circle will be closer to the box. Now, what do box... Yes, please.
I think the outlier is above the maximum.
Yes, it's the maximum non-outlier if you want. Yeah. So because we have a minimum and a maximum, but then one value is very far from the, if you want, from the bulk. Yeah, I will come back to that in a little bit. If you want, yes, that's a good point. It's the maximum non-outlier if you want. So the box plot will tell me if my data are symmetrical. So I look at the box plot. If I see the median, so the line in the middle of the box plot is the median. Yes, as I have here. So if the median is in the middle of the box and the whiskers, those 2 lines outside the box are called whiskers, are of similar lengths, then I can tell that my data are symmetrical. Now, mainly, the box plot is used to detect outliers. So if I see that any software has any circles outside the box plot, this means I have outliers in my data. Now, it also tells me about the variability in my data, and it's obvious because I have quartiles in it, and the quartiles are the measures of variability, and also the minimum and the maximum, which are my range. So if I have a great amount of variability, I have a long box and long whiskers. If I don't have a lot of variability, then they will be short. And we use box plots. One of the uses of a box plot is to compare variability. And to do this, we do side-by-side box plots. If I look, for example, at these 2 box plots, it's the box plot of age for males, and next to it, a box plot of age for females. So first, I see that both are not symmetrical, with a more skew for females. If you see the box for females, I have the lower whisker, it's much longer than the other, same for the box. The median is not in the middle. Now for the variability, I would say they're comparable a little bit. There are some difference in variability also, and I can also see here one more thing, is that the median age for female is much higher for the median age for males. And I can also see here, by just looking at this plot, that I have an outliers in the female values. Okay, it's about time. I have been talking about outliers maybe since the first slides. It's about time to say what is an outlier. So outliers are the observations that stand off away from the body of the distribution. So I have the bulk of my data somewhere, and then one data point is really far from the others. Now, in many situations, they can be the most informative observation of the data. However, in many other situations, they are just an error. Now, sometimes it's clear to see an error. If you see an age of 999, this is not an outlier. This is actually an error. But, or if you see males and females as 1s and 2s, and then you see a 5, you don't have a category 5. This is not an outlier. This is clearly an error. But in many situations, it is an outlier. For example, if everybody in your sample has blood pressure systolic between 120 and then 160, and then you see somebody 270, this is not an error. This is an actual blood pressure that is plausible. But why this person particularly had this very far blood pressure from the other, then this will be considered as an outlier. In situations where you have an outliers in the data, you have to keep in mind that you cannot remove it. Okay, I'm done with it, I'm fine, let me go on. You should do the analysis with the outlier and without it, and compare your results. If you have the same results, this is good. If you don't, then you compare and interpret both. And this is here an example. This is a meta-analysis when they did the analysis twice. One with the full sample, including all observations, and another analysis with the outliers removed. So they removed the values that were considered as outliers and redid the analysis and compared the results. Questions? So now mainly descriptive statistics is about the whole sample, the variable that represents the whole sample, but in many situations what we care about is actually relationships between two or more variables. So when we describe relationships, we have to also keep in mind the types of the variables. For example, you might be interested in the relationship between vitamin D levels and cognitive performance, or between parity, whether those who has a child before or women who are having their first deliveries, and it's associated with the request for epidural. So when we describe relationships, again we look at the types of the variables. If we have two variables that are quantitative and I want to describe their relationship, the measure to use here is the correlation coefficient, Pearson correlation coefficient. It is represented by the letter R universally. Sometimes you see it in capital, sometimes you see it in lower letter, more in lower letter. So this index, it measures the strength and the association of the linear association between two quantitative variables. This is a measure between -1 and +1. It does not have any unit of measurement. It's just a number, but it is sensitive to outliers. To interpret this R, one thing you look at is the sign of it. If it is a positive number, this means I have a positive relationship. A positive relationship will mean that my two variables, they move up or down at the same time. So high values of one variable are associated with high values of the other variable. If the correlation coefficient is a negative number, then I have a negative relationships, which means as one variable increases, the other variable decreases. So this is about the direction of the relationship between the two variables. Another thing I look at when I compute the correlation coefficient is the number, the actual number, the amount. If it is close to 1 or if it's close to -1. The closer to 1 and -1, this means the stronger the relationship. But had it been positive or negative, the strength of the relationship, it is described by the absolute value of the R. Now there are several rules of thumb and several guidelines, but it's difficult to offer one for you that you consider. If absolute value of R less than 0.5, then we say it's a weak relationship. Between 0.5 and 0.7, there's a moderate, and above 0.7, it's strong. There are several guidelines. What I usually use is less than 0.6 is considered weak, and then between 0.6 and 0.8, moderate. More than 0.8, it's strong, but some people might think this is very conservative. So I would leave actually this depending on the actual relationship you are studying. If you look at a couple of examples for the correlation, for example, if you are finding the correlation between the levels of depression and life satisfaction, and here I remind you that if I'm doing a correlation coefficient between those two variables, that means levels of depression, I'm measuring them on a scale. It's not depressed, the level. So for example, I do the Beck Depression Index, I come up with scores for patients. Same for life satisfaction. If I got here a -0.75, again, I'm going to call it strong, but again, some other people might call it moderate, so I'm leaving this for now. But it is a negative relationship. It has a negative sign. So it means that subjects who have high levels of depression are associated, have actually a lower life satisfaction. If I look in the second example, the very typical example, age and systolic blood pressure, in this situation, I have a positive relationship. So older individuals have actually higher systolic blood pressure. So Pearson correlation, it is used for relationships between quantitative variables and normally distributed variables. Now, if you have skewed data, Or if you have ordinal data, for example, pain, on a pain scale from 1 to 10, you can find correlations between those using Spearman's correlation. The Spearman rank correlation, it's also denoted by RS. It is actually Pearson correlation. It's Pearson's correlation, but on the ranks of the data values. So instead of having the data value itself, 50, 60, 70 years, you can have 1, 2, 3 instead. It's the rank of that value in the data set. It is a number between -1 and 1. A lot of people interpret it like Pearson, the same, but it's not exactly the same here, again, because you are doing a correlation on ranks and not exactly on the values. If you look at this example here, associations between quantitative variables were evaluated using Pearson correlation or Spearman, and they mentioned to you that Spearman correlation was used for non-normally distributed variables. Now, correlation is one of the most misused statistical terms. Whenever we say correlation, don't be confused with causation. Correlation does not at all mean causation. If variable x is correlated with variable y, this does not mean x is causing y. Maybe y is causing x, or maybe both are resulting from some other variable z. So correlation only means that there is an association between the two variables, but no causation is implied here. If we move now to the association between two categorical variables, this is described by a series of risk indexes. There are the relative risk, the absolute risk, the odds ratio, the risk reduction, and so on. I will only discuss here one, which is the relative risk, and I will discuss it for situations when my two categorical variables are dichotomous. A dichotomous variable means that it takes only two groups. So, for example, gender, male, female. If I want to use marital status as dichotomous, I can, but then I will do it as married, non-married. In the situations when we do indexes of risk, our two variables actually are, one is risk factor or an intervention. So intervention versus control, or exposed versus non-exposed. This will be one of my variables. And the second variable of interest will be my outcome, which is I have the disease or I don't have the disease. So these are the typical variables of interest when we talk about indexes of risk, the risk and the outcome. Now, the relative risk is the most, it's not the most, but it's a very used index of describing relationship between two categorical variables, and it's the easiest maybe to interpret. The relative risk addresses the question, how many times more likely are those who are exposed to become diseased than those who are not exposed? It's a number. If it's equal to 1, it means the risk is the same between the two groups. So exposed and non-exposed are equally likely to have the disease. If the relative risk is a number that is less than 1, this means that the event of interest, the outcome, is less likely to occur in the group who are exposed. In this situation, we call a protective factor instead of a risk factor. And if the relative risk is greater than 1, then here we can call whatever risk we are using as a real risk, and this means that it's more likely, the event of interest is more likely to occur in the exposed group. If you look at this example here, so these are the typical table we use when we compute indexes of risk. These are called contingency tables. So it's a frequency table, but for two variables. I have one variable in the columns and the other variable in the rows. And in the cells, I have the counts that are falling within each combination. So the column usually represents the outcome. And in our situation of indexes of risk, we have, again, two. Have the outcome, does not have the outcome. And the risk factor, which is, or the intervention status, smoke, did not smoke. So these are called 2 by 2 tables. In this situation, if you compute the relative risk, we get a 4.4. So this number will mean that those who smoke are 4.4 times as likely to develop my outcome, which is lung cancer, compared to those who do not smoke. questions? As a summary, descriptive statistics is a summarization of the data. You are only having your data and you are presenting it in a nice, clear, and understandable way. This is indeed the most basic form of statistics, and that's why the lecture is really short. However, this is the foundation. So you start with descriptive statistics. If you don't see anything interesting, you stop here. If, for example, I'm interested in the relative risk here and I get a 1.02, then I don't even care about moving forward. But whenever you see something interesting happening in the descriptive statistics, you see something going on, then you bother moving further and doing some additional analysis. Any questions? Mona?
Thank you. Thank you. Straightforward.
It's basic.